Hello, my name is Nigel Bowden. I'd like to welcome you to episode 12 of the Wi-Fi for Beginners podcast. This is a series of podcasts discussing the fundamentals of wireless LAN networking. In each episode, we'll take a look at a different aspect of Wi-Fi to help build your knowledge and understanding of wireless LAN networks. With each episode, there's an accompanying set of slides which will describe the topics covered in the episode. You don't need to review these as you're listening to the podcast, but they can be useful to review the material that we discuss and provide a few visual aids so you can more fully understand some of the concepts and equipment described. All recordings and supporting materials can be found at my website, which is wififorbeginners.com, and I'd particularly like to invite you to join our mailing list. You can see a little join up form there on the right hand side of each page where you can join up for the mailing list and hear about forthcoming episodes and other useful material that we're going to make available as the series progresses. We're actually on module 4 of the series. This is actually the third episode of module 4. Module 4 is all about more advanced RF concepts, so as this is episode 12, we need to go back to episode number 10 to hear the start of this particular module. And we've already covered quite a bit of ground, but we're just going to finish off this topic now with a bit of a look at the 5 Gigahertz band and a few words around RF design. Before we jump into that though, I'm just going to do a very quick recap on what we covered in the last episode, just to bring you back up to speed so that you'll get your memory refreshed and we'll be able to dive into the new content straight away. So in the last episode we took a very brief look at what we mean by a channel. A radio system can't actually operate on a single frequency to be able to convey data. We actually need a small range of frequencies so that we can apply a modulation technique, and as we've got a range of frequencies we can apply modulation and transfer data. Normally when we're talking about a channel, it's a subset of the entire frequency band that we're using, so it's just a small chunk of that particular frequency band. It's usually got a lower and an upper frequency which are specified, and the difference between the lower and upper frequencies is the channel width. And normally in wireless LAN systems we start off at least 20 megahertz channel widths, but we can actually use multiples of that. We can use 20 megahertz, 40 megahertz, 80 megahertz and 160 megahertz. We also went on to talk about the two main Wi-Fi bands which are available across many parts of the globe. We've got the 2.4 Gigahertz band and the 5 Gigahertz band that we've mentioned on a number of occasions before, and these are generally fairly globally available around the world. The only caveat around that is that the actual channels available for use on the two bands may vary from country to country, and this may be due to existing services which already occupy some of those channels. Fairly commonly across the globe on the 2.4 Gigahertz band we've got maybe 11 channels available, or 13 in some parts of the globe, but when we actually start talking about the 5 Gigahertz band we start to run into some fairly substantial differences between countries around the globe. We also took a very quick look at some of the regulatory bodies around the world who actually decide which channels can be used on the wireless LAN bands in different parts of the world. We've got a global organisation which is the ITU, the International Telecommunications Union, and down at regional and country levels we've got bodies such as the FCC, we've got ETSI in Europe and Ofcom in the UK, and each country will have their own local wireless regulatory body. And we also said that it's very important to know the regulations which govern your country. You need to know exactly which channels can be used and what the limits are on things like transmit powers and the use of wireless LAN equipment indoors and outdoors. We then took a look at the 2.4 Gigahertz band, which was until recently the most popular band for wireless LAN devices due to the low cost of components and the initial mass adoption on that band. There's definitely more of a move towards the 5 Gigahertz band at the moment, and that's becoming the band of choice for mission critical applications. The problem with the 2.4 Gigahertz band is that we actually have usually around about 11 or 13 channels available for use, but because the actual spacing between each of the channels is only 5 megahertz, and we generally need at least 20 megahertz for wireless LAN devices to communicate, then we can't actually use each of the channels that are adjacent to each other. So we can't use channel 1 and 2, channel 2 and 3, channel 3 and 4. You get the idea, all the way up to channel 11 or 13. We actually have to space the channels which we use to make sure we have non-overlapping channels, and this is where we derive the convention of using channels 1, 6 and 11 as the general standard that most wireless LAN professionals tend to use when deploying equipment on the 2.4 gigahertz band. So this only gives us 3 usable channels to use, which makes it very difficult to use many APs in the same area on the 2.4 gigahertz band, because when we have 2 APs that are using the same channel, this gives us co-channel interference, and if they can hear each other, then they're actually contending for the available bandwidth available to stations which are using the same channel. Another important concept, if we do actually use 2 channels which are adjacent to each other, if we try and use channels 1 and 2, or maybe 1 and 3, 1 and 4, then they are actually considered to be adjacent to each other, and this causes adjacent channel interference, which is going to cause us some fairly significant problems in terms of errors and retransmissions for our wireless LAN traffic. Okay, so after that review of the material we covered in the last podcast, it's time to move on to some new material where we'll continue talking about some more advanced RF topics. And we're going to start by looking at the 5 gigahertz band in a little bit more detail. If you are following along with the slides, you can take a look at slide number 29, where I've actually provided a graphic which gives you a breakdown of the different channels which are available for the 5 gigahertz band. The actual graphic I've shown is for North America, but it's a fairly similar number of channels available in different countries around the world. You can see on first glance there's many more channels available on the 5 gigahertz band than there are on the 2.4 gigahertz band. In the example of North America, we've certainly got in excess of 20 channels which are available, and here in the UK we've got around 19 available that we can use at this point in time. In the graphic you can also see the way we can bond together channels into 40 megahertz, 80 megahertz and 160 megahertz channel widths, which is made possible by some of the later 802.11 amendments such as 802.11n and 802.11ac. So, as we previously said, the 5 gigahertz band has grown significantly in popularity over recent years, and it's pretty much now the band of choice for mission critical applications. We generally have around about 20 channels available on the 5 gigahertz band. It varies from region to region around the world, but the important thing to note about 5 gigahertz band is that we can actually use all of the channels that are allocated to us. If you remember back to the 2.4 gigahertz band, we had maybe 11 or 13 channels available. We couldn't actually use adjacent channels there. We had to split them up and just use channels 1, 6 and 11. We had to leave space between each of the channels that we were using because of the requirement for 20 megahertz channel widths. Well, on the 5 gigahertz band, each of the channels that are allocated are already 20 megahertz apart, so we can actually use each channel that's allocated. Channel numbering on the 5 gigahertz band is a little bit different to the 2.4 gigahertz band. 2.4 gigahertz band channel starts at channel 1 and they go up through 2, 3, 4 all the way up to 11 or 13. But with the 5 gigahertz band they start at channel 36, the next one's channel 40, channel 44, 48, etc. The channel numbering does vary slightly as we move through the different 5 gigahertz sub-bands which are allocated, but they're all separated by increments of 4, and we get a 20 megahertz channel width that we can use for each one, as I say, so we can actually use all of the channels allocated, and this gives us much higher levels of capacity. We can deploy many more APs in a facility which are using unique channel numbers, so that we can have far less issues with co-channel interference and APs and clients contending for the same channel, because we can use many more unique channel numbers. And as I said previously, 5 gigahertz now is the preferential band to use for mission critical applications rather than using 2.4 gigahertz because of the various limitations of the band that we've already discussed. If we consider the 2.4 and 5 gigahertz bands, they're both in a fairly similar area of the RF spectrum. They're both in the gigahertz range, but even though they're a similar area, they've actually got very slightly different characteristics. If you remember We talked previously about the fact that as frequency of a signal rises, then its characteristics vary. We can start to consider that as we get higher frequencies, it maybe takes on more and more of the characteristics of light. And certainly with 5 gigahertz compared to the 2.4 gigahertz band, signals in this range are subject to far higher levels of attenuation due to obstructions in the environment such as walls and doors. We've also talked previously about the concept of free space loss, and free space loss describes the way that an RF signal naturally reduces in power as we move away from the source of the RF signal, so that if we're actually measuring signal levels of a wireless access point, as we move further and further away, the signal naturally becomes lower and lower. And what we actually find is on the 5 gigahertz band, RF signal levels drop off more rapidly on the 5 gigahertz band compared to the 2.4 gigahertz band. So this gives us the effect that if we're standing at a particular distance from a wireless access point, and the two radios in the access point are both transmitting at the same signal level, we will actually find that the received signal power level on the 5 gigahertz band is actually lower than on the 2.4 gigahertz band, and this actually effectively gives us smaller cell sizes when we're comparing the 5 gigahertz band to the 2.4 gigahertz band. On the face of it, this provides the 5 gigahertz band with a significant disadvantage when we're comparing it to the 2.4 gigahertz band, and certainly in the early days of wireless LAN networks, when one of the key requirements was as much coverage as possible, then 5 gigahertz certainly wasn't the primary choice. But as we're moving into an age of requiring more and more wireless access points packed into smaller and smaller spaces, we have to pack in many more access points across the floor of each office, for instance, where we're deploying a wireless LAN to give us the capacity that we need, then certainly having naturally smaller cell sizes is actually a significant advantage, because we can actually pack in many more AP cells before we start running into problems such as co-channel interference. And also the tendency of 5 gigahertz signals to be more naturally attenuated by obstructions in the environment certainly helps as well in reducing cell sizes, providing more containment of RF signals, and again this all helps in mitigating things such as co-channel interference. If you've got access to the slides, you might like to take a look at slide number 32, where I've actually shown another graphic. And this one is demonstrating how we might plan our channels for the 5 gigahertz band. And if you contrast this with the previous graphic of a channel plan for the 2.4 gigahertz band, you see the significant difference. On the 2.4 gigahertz band, we could only ever have a cluster of 3 cells before we were actually hitting channel reuse. We were using channel 1, 6 and 11, and we were trying very hard not to get 2 cells that were adjacent to each other which were using the same channel, because this causes co-channel interference problems and reduces our overall capacity. But if you contrast this with the 5 gigahertz band, looking at slide number 32, you can see we've actually got quite a number of cells there, and they're all using unique channels. There is no reuse of channels at all. We're assuming 20 megahertz channels here, so that we have the full range of channels available. If we start doubling up channels to 40 megahertz or increasing them to 80 megahertz channels, we actually have fewer unique channels available. But assuming we're using 20 megahertz channels, we've got maybe upwards of 20 channels that we can use. So we obviously can have many AP cells before we start having to reuse the same channel again and start to run into co-channel interference type problems. Again, as I said previously, when we're talking about regulatory bodies, it is absolutely key to understand the channels which are available in your particular region. Certainly with the 5 gigahertz band, there are many more variations and many more restrictions which apply. That there are many more topics I could talk about on the 5 gigahertz band, but unfortunately we've got to sort of keep this to a beginner's guide. But there are certainly things such as coexistence with radar systems. It's a facility called DFS, dynamic frequency selection, and certainly the power levels which can be used indoors and outdoors vary greatly in different parts of the world. The actual number of channels which are available vary enormously across the globe, and unfortunately it's very difficult to give generic information about the 5 gigahertz band because there is such a variety, and it's absolutely key to understand in your particular country which channels can be used and which ones are actually out of bounds for usage, as I say, for your particular country. So now we've spoken about the 2.4 gigahertz and the 5 gigahertz band. There's one important fact about both of those bands, which are used for wireless LANs, that we need to bear in mind. They're actually classified as unlicensed spectrum. You may have heard this term bandied about before, and I think I may have even mentioned it previously and in prior episodes of the podcast. But what do we actually mean by unlicensed spectrum? What do they mean by unlicensed frequency bands that are used by wireless LAN networks? So just to give you a little bit of background information, a lot of the RF spectrum, a lot of the radio frequency bands which are used require a permit or a license to actually use them. And if you think about services such as commercial radio services, the frequency bands that are used by emergency services like police, fire services, cellular providers provide cellular phone networks, people like radio hams. There's a whole host of people who use a whole variety of different frequency bands across the entire RF spectrum, and to actually use a particular set of frequencies or a particular band, then they actually have to have some sort of permit or license to use those, and there's normally a fairly significant cost associated with that as well. They have to pay an annual license fee to use those particular frequencies, and also, as well as having to pay for a license, they also have to ensure that they've got very tight controls, very tight technical controls in place to ensure that they stay well within their frequency bands and they don't cause any sort of interference to neighbouring services which may be on nearby frequencies. And these are very stringently enforced by local regulatory bodies who enforce the use of radio frequency spectrum in each particular country. So the good thing about the bands used for wireless LANs is that they are in fact unlicensed spectrum, which means that you don't need a license to use them. You don't have to pay for a license. You can just buy some wireless LAN equipment, fire it up and start using it to provide the wireless LAN services that you require. Equipment that's used on these bands has to operate within certain restrictions. There are certain power settings and a variety of technical restrictions, but these are built into the wireless LAN equipment itself, and it's very difficult to actually get the equipment to operate outside of these restrictions, so it makes it very easy for pretty much anybody to deploy a basic wireless LAN network. So it gives us pretty easy to use, easy to deploy, commoditized mass market devices that we can use to quickly and easily deploy wireless LAN networks. Unfortunately, as it's unlicensed spectrum, there is a price to pay for all of this ease of use and the availability of the spectrum to so many people and organisations. So because of the lack of barriers to use of the spectrum, you don't have to buy a licence for it. Anybody can jump on there and fire up their wireless LAN equipment and even other types of devices which are also allowed to use the same frequency bands. So we're more likely to suffer with interferers on the same band or even the same channel. So you could in fact install a wireless LAN network, and then you could have a neighbouring company or even one of your neighbours at home who fire up their wireless LAN equipment, use the same channels and provides contention over the air, so you're both competing to use the same frequency spectrum. And as I say, there are also other services and devices which can use the band which are non-wireless LAN devices. You've got things like Bluetooth devices, you've got baby monitors, microwave ovens, you've got security cameras. There's even the prospect of having some cellular providers providing LTE services on 5 gigahertz in the near future. So there's a whole variety of other services and devices which can use the same unlicensed spectrum, because anybody can use it. It's available for everyone to use as long as they stick within certain technical parameters. Then they're free to use it pretty much for whatever they like. And the 2.4 gigahertz band has been particularly successful. We've spoke about this previously. It was the most popular wireless LAN band because of the low cost of components and the high uptake of that particular frequency band, and there's in fact so much going on that particular band now. It's actually started to be called the junk band, as well as wireless LAN services. We've got a whole host of other non-wireless LAN devices which are jumping on there, using it and making it very, very difficult to provide any sort of quality service for a wireless LAN on there. So realistically, you need to bear in mind when you're deploying a wireless LAN, the 2.4 gigahertz band is very much a second-class citizen. It's not a good choice when you need performance in professional environments, as well as the limited channels that we've got. We've already spoke about before. We're limited to 3 channels, 1, 6 and 11, but also there are many interferers on that band which are certainly going to impact your wireless LAN, and certainly not going to give you the best performance that you'd like to achieve. And we'd certainly be looking at using the 5 gigahertz band for any sort of mission critical type applications. So finally, for this particular module, just want to spend a few moments talking about RF design and the importance of good RF design. I really can't stress this enough. This is probably one of the areas of wireless LAN networking that is overlooked the most, and people probably don't give it the same priority that it requires. And so I really just wanted to spend a few moments talking about it and stress the importance. So if you think about the 802.11 standard itself, it operates at layers 1 and 2 of the OSI stack, with obviously layer 1 being our physical layer. And when we're talking about the RF design of a network, we're very much talking about the layer 1 side of things. And so when we're designing our network, we have to be employing good RF design principles. We need to understand RF behavior, which I've tried to talk a little bit about in the couple of RF modules that we've had. You need to understand things like propagation, understand the nature of interference, understand things like RF power levels, things like antenna choice, which is the best antenna choice for your particular application, things like band choice, which band is going to be the best for the environment and the applications that you have. We've previously spoken about the differences between 2.4 and 5 gigahertz bands, and very importantly, you really need to understand the RF restrictions which apply to your country. Which particular channels can you use, what power levels can you use, which can be used indoors, outdoors, this type of thing. And a really good analogy, I think, which sort of highlights the importance of good RF design principles. If you think back to an Ethernet switched network, if you think about layer 1 there, we're talking about our basic cabling. From each switch port, we've got cabling through to maybe a data point where we connect all of our stations. We maybe connect a laptop or a PC, some other sort of device which requires an Ethernet connection. So if you just imagine the impact on that network if you employed poor layer 1 design principles, if you didn't have good quality cabling from your devices through to your switch ports. Just imagine what that would be like, running with poor quality cabling, constantly be suffering with lots of errors, retransmissions and very, very poor performance for your client devices. And exactly the same issue exists without good RF design. If a wireless LAN is deployed without factors such as correct channel choice, power level settings, and minimizing things such as co-channel interference, then the network itself is going to run very poorly, and we're never going to be able to achieve the high levels of performance we'd expect from a mission critical network. And there's no getting away from the fact that with a poor physical design, poor layer 1 design, we're always going to end up with poor network design. No other features within wireless LAN equipment can mitigate or rescue a wireless LAN that has had poor RF design. There's just no way of working around that. We've got some systems which have got features such as auto RF, which is supposed to tune an RF environment to try and optimize it to improve the performance of a wireless LAN, but even these simply can't work around a poor RF design. They can do things like changing RF power, they can change channel settings, but they're still constrained by the environment that they've been deployed into. And if that environment hasn't been designed properly, there's just no way of making that wireless LAN operate in an optimal fashion. If you think back to the Ethernet analogy that we talked about, just imagine if you had poor quality cabling. It doesn't matter how high quality your switches or the devices you connected to the switch ports, with that poor quality cabling in the way, you're always going to have a very poorly performing network. So I think the final message I'd like to leave you with is that the whole of the RF theory and the RF design element of wireless LANs is probably the most challenging area, especially for people who are transitioning from wired type networking to study wireless LANs. It's definitely quite a big challenge. It's a fairly new area for many people, but I think it is the area which is going to differentiate you from other wireless engineers. There are many wireless engineers about who are very good at configuring a particular vendor's equipment to get it to provide the the basic services that they need, but they don't have the necessary background to really effectively provide a good RF design, so they've got that good layer one for a wireless LAN network. So I would strongly encourage you to bite the bullet and really get up to speed on RF theory and RF design as much as possible to provide you with a really significant advantage in your wireless LAN career. So we've reached the end of module 4, and it's been a fairly lengthy module. It's been some pretty heavy going, to be honest, but certainly been some very valuable information here, which is certainly going to help you with your wireless LAN career. And if you can digest all of this information and certainly build on it through other sources of study, it's certainly going to stand you in very good stead. I'm going to just quickly summarize what we've covered in this module, but just before I do, just want to remind you to get along to my website, which is wififorbeginners.com. I'd like to strongly encourage you as well to sign up to the mailing list I've provided there. It's going to provide more information for you in the future about forthcoming episodes and other sources of information, maybe some offers, things that I can get arranged as I gradually make more material available over time. And don't forget, you can also download all of the audio programs, you can download the slides, and there's some quizzes there so you can test your knowledge of the various modules that we've covered through this podcast series. So just to summarize, we started off at the beginning of the module doing a very quick review of module 2, where we talked about basic RF concepts such as frequency, talked about RF transmission in general, things like frequency multipliers, the different frequency bands that we may use, and we also talked about things such as free space loss. We also then talked about the basics of an RF system. We talked about the fact that we need a transmitter and a receiving station, and these need to be on the same frequency in order to be able to hear each other. We also talked about the half duplex nature of an RF system, where we've got one transmitter which is transmitting, and all of the stations that are within its coverage area can hear, but only one transmitter can be transmitting at any point in time, and all receivers have to be in a receive mode. They can only talk back to the transmitter when it's finished its transmission. We considered a walkie-talkie system to demonstrate some of the features and functions of an RF system that we talked about. We considered how all walkie-talkies in a system must all be on the same channel so that they can hear each other. And we also discussed the half duplex nature of a walkie-talkie system. Each person using the walkie-talkie can press the button when they have some information to send, and all of the stations must be in receive mode, so only one person can actually press the button and transmit at any point in time. If we do get two people who both press the transmit button, we actually get simultaneous transmitters sending their information, and all receivers will just get a garbled message and won't actually be able to understand the information that's being sent. And this is a very good analogy for the way RF systems such as wireless LAN networks operate. We also talked briefly about co-channel interference, and this is when we've got devices which are attempting to use the same channel at the same time, which can lead to the type of interference we just talked about in the walkie-talkie system. And in the context of a wireless LAN, co-channel interference also describes the contention that we have for a particular channel if we have many stations, such as many access points, all trying to use the same channel. We also talked briefly about CSMA-CA, which is Carrier Sense Multiple Access with Collision Avoidance. In wireless LANs, we don't actually have collision detection that we have in Ethernet networks, and so we have to avoid collisions rather than detect them using a carrier sense mechanism, and to use random countdowns to try and avoid stations transmitting at the same time. Also, we have no level of certainty within a wireless LAN whether or not a transmitted frame was actually received at its destination. Because we have no collision detection, we don't know if there was a collision with any other signals in the air at the time the frame was sent. So each frame in a wireless LAN system has to be explicitly acknowledged to verify that it was correctly received by a receiver. We also spent some time looking at RF contention in wireless LAN systems. Wireless LANs are fundamentally a contended medium. That means that all stations trying to use the RF medium have to wait their turn before they can actually transmit any data. The stations on a wireless LAN all share the limited airtime which is available, so the bandwidth which is available over the air between receivers and transmitters is shared equally amongst all stations within a coverage area, and this could be something like the cell of a wireless access point. And as we get more stations which move into that coverage area, we're actually increasing the contention domain. So as we get more stations contending for the same amount of bandwidth over the air, then less and less bandwidth is available to each station. We also briefly talked about the concept of channels. We mentioned again that we can't actually use just a single frequency to convey data. We actually need a small range of frequencies, and we've usually got a lower and an upper frequency to give us the width of our channel. And having this small chunk of the frequency band allows us to use a modulation technique which allows us to convey data over the RF link. We also talked briefly about the two Wi-Fi bands which are generally available across most of the globe. We've got the 2.4 and the 5 gigahertz bands, and we also talked about the fact that although these bands are available in most areas of the globe, the actual implementation specific details in each country will vary from country to country, and this can include things such as the channels which are available, power settings, things like that. We also talked very briefly about the regulatory bodies which determine the channels which can be used in each part of the world. We talked about the ITU at the top level, which gives a global spectrum policy, and then we also talked down at regional and country levels. We've got regulatory bodies such as the FCC and ETSI. We also talked about the fact that the 2.4 gigahertz band is still pretty heavily used, but unfortunately only gives us 3 usable channels, so we end up with very poor co-channel interference on that particular band. It's got a very high noise floor, and it's a very poor choice for mission critical applications. We also talked about the 5 gigahertz band, which generally has far more usable channels in most parts of the world. This allows us to have lower levels of co-channel interference, as we can have more APs running on unique channel settings. And we also discussed how the 5 gigahertz band gives us much better propagation characteristics for today's higher density environments. We also talked briefly about unlicensed spectrum. Licensed spectrum is a radio frequency spectrum which is subject to very tight controls, and it's limited to services which have actually purchased some sort of license or permit to use that particular part of the RF spectrum. In contrast, unlicensed spectrum can be pretty much used by anybody, but unfortunately because of this open access to anybody to be used without having to purchase any sort of license or permit, then it's subject to interference from neighbouring networks and other services which may use that particular part of the spectrum, but the advantage is it does allow a low-cost equipment and very rapid deployment. And then finally I touched on the importance of radio frequency design for wireless LANs. There's no getting away from the fact that if we had bad RF design, if we've got a bad layer 1 design, then we are always going to have bad wireless LAN performance. There's no amount of vendor options or features which is going to allow us to work around a bad RF design. And that really is the end of this particular module. As I say, just like to remind you to pop along to the website, which is wififorbeginners.com, if you'd like to download any of this supporting material for the podcast. I hope this particular module has been of benefit to you and you've gained some useful information from listening to the 3 episodes in this particular module. In the next module of the podcast series, we'll be taking a look at wireless clients. We've talked an awful lot about wireless infrastructure equipment, RF theory, but the whole purpose of wireless LAN networks is to actually allow the transfer of data between wireless LAN clients. They are the most important thing on the wireless LAN network, and they're the reason that it exists. It allows users to communicate to each other and to services, and so we'll be taking a pretty detailed look at wireless LAN clients in the next module. So thank you very much for joining me. I look forward to joining you again soon on the next episode of the Wi-Fi for Beginners podcast.